Alright, so this is going to be the video for the hydrates that we covered. So first we're going to learn about naming hydrates, which is relatively easy. You just name, we already learned how to name the salt part of it, so that's copper sulfate. And then we add a prefix based on the number of waters we have, so 5 would be penta. And then the water bit is what we are going to call a hydrate. So hydrates are chemicals which have a dot and then a number of waters after that. They can have any number of waters possible, but that's just because water just attaches itself to the salt, and therefore these are called hydrates because they're hydrated, as in they have water attached to them. So I'm not going to write out all of this. So this is zinc sulfate, heptahydrate, calcium chloride, dihydrate, sodium carbonate, decahydrate, right? This is barium hydroxide, octahydrate. This one is iron acetate, tetrahydrate, and zinc nitrate, hexahydrate. So using a prefix chart at the back of your periodic table, you should be able to name all these compounds relatively easily. So now we're going to look at how to calculate how much water is present in a hydrate experimentally. So we don't know, that's why we have a little X here, because saying unknown. And we usually, 100 grams is a bit much. We usually don't start with 100 grams, but let's say for this, just for initial calculation, we're going to start with 100 grams. So we have 100 grams of this hydrated salt. We are going to evaporate the water, and after that, what we're left with is the anhydrous salt, which is just the salt without the water bit. So that's just MgSO4 would be the anhydrous salt. So we have 48.8 grams of anhydrous salt left, which means we have evaporated 100 minus 48.8, which is 51.2 grams of water. We have successfully evaporated from this compound. Okay, so now that we know our mass of water, we're going to go here. We're going to basically do the same thing we did for empirical formula calculations, except we're going to modify it for water. So we know that the magnesium, the hydrated salt, is basically composed of two parts. So once we heat it up, it splits up into the anhydrous salt, which is part number 1, anhydrous salt, which is MgSO4, and it also splits up into how much water it had. So that's the second part, which is the water, which is XH2O. So again, this is the mole ratio that's given over here. So we're only going to calculate the molar mass of water, and put that in brackets just in case. Molar mass of MgSO4 from the periodic table, we get to be 120.36 because we're adding 1 magnesium, 1 sulfur, and 4 oxygen. So we are given the mass in 100 grams to be 48.8, 51.2. We can calculate number of moles by doing the division. It's a 2.84. And now again, this is our smallest number, so we're going to divide both by 0.405. And we are obtain 1 and 7. So this 7 here is basically giving us what our X is. Our formula is now MgSO4.7 H2O, magnesium sulfate, heptahydrate is our chemical formula. And now we have to calculate the percent of water in the compound. Now we've done this, the beginning of this week, last week, I don't know, sometime we did a calculation for percent composition using the actual and the theoretical values, and we're going to repeat that calculation. So first we have to calculate our experimental percent, which is our actual mass of water divided by our mass of compound, total mass, times 100%. Our mass of water was 51.2, mass of compound was 100 grams. Note that that's the total mass of the compound, times 100% is just 51.2%. Nice and easy. And then we will do our theoretical percent, which is a little bit different because we are using the molar mass of water divided by molar mass of compound times 100%. So our molar mass of water we can calculate to be 7 times 18.01 because there's 7 waters. We do have to take the 7 because now we know exactly how many waters there are. Here we didn't because we don't take the X in our calculations of water here because we're calculating the 7. That's what we're getting. But now that we know the 7, the molar mass of water in this entire compound, we do have to multiply by 7. And then molar mass of compound will be this, the same value, plus the whatever magnesium sulfate we had, which is actually going to be equal to 126.14 divided by 246.5 times 100%. I forgot the times 100% here. And this gives us 51.17%. So very close, but not quite, but that's okay. Because now we can use that to calculate our percent error, which is theoretical minus experimental divided by theoretical times 100%. Theoretical was 51.17 minus 51.20 divided by 51.17, 0.03 divided by 51.17 times 100%, which is a very small percent error. It's actually super small. That is very rare. In actual lab conditions, I just made up these values so that they would actually work. So I got a super small percent error, but in a lab, you will have a much larger percent error, and we have to talk about the sources of error that can occur in a lab. And some of the sources of error that can occur is that the compound is the reaction may not be completely complete, so as in all the water has not been evaporated, leading to some water left in this 48.8 grams. There could also be perhaps other compounds that are being formed when you heat up the magnesium sulfate. Some of the magnesium sulfate might break down, and there's a lot of sources for error that can happen in a lab, and so I will let you think about some others for our formal lab report. All right, I will see you in class.